This technical training videotape is designed to familiarize you with oscilloscope operation to measure DC and AC signals. You will find the accompanying technical training manual a valuable resource as you view this videotape. Please consult it often. I'm Professor Richard Kent, and I'll be your instructor.
And I'm Janie Kent. I'll be the instructor's assistant.
For the next hour or so, we'll provide you with detailed technical content that'll teach you the fundamentals of using an oscilloscope. There are safety-related issues you need to be concerned about before operating the oscilloscope. Do not use it if it appears to be damaged in any way. Caution, there is an electrical shock hazard when operating electronic test equipment. Particularly use extreme caution when working around voltages greater than 60 volts DC or 30 volts RMS, and never operate the oscilloscope or other instruments in flammable atmospheres. Also, never exceed the input voltage rating to the oscilloscope. It could place you and the scope in harm's way. Always connect the oscilloscope to an AC supply voltage that matches the voltage requirements of the instrument. You can find this information out on the back of the oscilloscope itself. You should always use the proper power cord, preferably the one supplied with the instrument, or at least obtain a suitable replacement. And never defeat the ground prong on the AC power plug. Also, never use cheater plugs. You'll put yourself at risk for a shock. Always use a properly grounded AC outlet, and never cut the ground prong off the AC line cord. Never connect the scope to equipment where the chassis presents a voltage relative to the ground. In most installations, the entry cable contains a ground wire that's connected to the service panel. This is the actual building ground. A ground rod is often used to establish a good ground. The service panel chassis is connected to the utility ground and the building ground. All outlets are fed off the panel and are thereby connected to this ground point. Hot chassis TV receivers are examples of electronic equipment using transformless designs. Use extreme caution at all times, and preferably an isolation transformer, as illustrated here. Note, there is no ground connection. In this case, it is acceptable to use a cheater plug, since the float is provided by the transformer. Caution, never expose the instrument to water. This can create a serious shock hazard. Electricity and water simply don't mix. Use extreme caution when working around machinery, especially where moving parts are present. Test probes and leads can get entangled, causing the possibility of strangling to you and damage to the instrument. The rule is keep everything in the clear. Remember, keep safety as your first concern. The front panel of an oscilloscope appears to be a very intimidating instrument to operate. Starting from the left, we have the actual main oscilloscope screen, which consists of a cathode ray tube in the case of an analog scope, and we have various beam controls as well as power controls. The oscilloscope we're featuring in this training video is a dual trace model. Therefore, it has two vertical input channels, a channel A and a channel B. The ability to display two signals simultaneously is met with ease with instruments of this caliber. As you see from a close examination of the front panel, there are a multitude of controls, knobs, and switches necessary to properly display a signal on the graticule. We'll concentrate on some of the basic functions first, working into more advanced aspects of the oscilloscope at a later time in the tape. We'll learn later in this program that each vertical channel has its own position and vertical attenuator controls, as well as its own unique BNC input. On the right side of the oscilloscope, we see the horizontal section of the oscilloscope. Here we'll find the horizontal position or X position control, as well as the horizontal sweep rate control, which is used to set the beam sweep speed. Let's begin by powering up the instrument. Every model has its own unique features for powering up the instrument, so consult your operating manual now. The particular model oscilloscope we're using here also has a backlight display which is adjustable by means of a potentiometer. The intensity control allows you to increase or decrease trace brightness. This is especially useful when working under varied ambient lighting situations. Rotating the intensity control clockwise increases trace brightness, while rotating it counterclockwise decreases it. You'll always want to select the minimum intensity needed for accurate measurements and to protect the CRT's phosphors from burning. You can then adjust the focus control for the sharpest trace possible. Keeping the trace focused will help you make razor-sharp measurements. Especially when setting up the instrument for the first time, you might have to trim the trace rotation a bit. An ordinary alignment tool makes this an easy job. Trace rotation is usually performed once and then forgotten. The coupling switch selects either AC or DC coupling. The ground switch effectively decouples the vertical input signal from the scope circuitry. This is particularly useful for setting the trace reference. Always make sure the calibrate or cal control is turned to the calibrate position. This control is usually located on the vertical attenuator control. Serious measurement errors can occur if you fail to set this control properly. Most vertical attenuator vernier controls have a click indent position so the operator knows when cal is activated. Both channel A and channel B have identical vertical position controls. The function of the vertical position control is to set the vertical position of the trace on the graticule. In the case of dual trace oscilloscopes, the vertical position of each trace can be set independently. On multiple channel oscilloscopes, such as 4-channel scopes, each vertical input has its own vertical position control. Note the smooth operation of the vertical position controls. This is indicative of a quality instrument that allows the operator to properly place the trace at any point on the screen. Depending upon the type of measurements being conducted, it may be necessary to position the trace reference at the top of the screen rather than at the bottom or center. For basic measurements, centering the trace at 0 reference in the center of the screen is a good place to begin. I can't stress enough, you must check, and recheck that the vertical attenuator vernier control is in the cal position. Otherwise, measurement accuracy will be seriously compromised. Most dual trace oscilloscopes allow the operator to select between alternate and chop modes for dual trace measurements. The alternate mode is preferred for high frequency signals, while chop is best for viewing slower waveforms. Here we see 2 traces being displayed on the same graticule simultaneously. Unfortunately, because the phosphor is of one color only, it's difficult to distinguish which one is channel A and which one is channel B. This is where measurement operator skills come into play. We can see here that each trace is independently positionable on the screen. Each vertical amplifier of the dual trace oscilloscope has its own BNC input connector. These BNC connectors are where you'll connect oscilloscope probes or test leads for making measurements. You'll note that each BNC connector is located typically beneath the vertical attenuator control for the respective channel. You should note that the vertical inputs share a common ground connection through the scope's chassis. Therefore, the ground of channel A is the same potential as that of channel B or the case ground of the instrument and the power line ground for the building. This is why it's so important to know the type of measurements you're getting into before actually taking them. Otherwise, you could place yourself at risk as well as the instrument by connecting the ground of the scope, which is ultimately connected to the building ground, across a live line that is referenced to ground. The vertical attenuator control functions much like the range switch of a volt-ohm milliamp meter. Both channels operate in identical fashions and allow the operator to select different vertical input sensitivities for each channel. Here the technician is verifying that the vertical attenuator vernier control is in the calibrate position. The horizontal position or X position control allows the operator to move the trace either to the left or to the right of the screen. A good place to start is with the control in the centered position. The horizontal sweep rate control or time-based selector allows the technician to choose a horizontal sweep rate for the beam. In the case of this 50 MHz scope, the horizontal time base can be varied from a slow speed setting of 0.5 seconds per division to a high speed setting of 0.1 microseconds per division. Additionally, a multiplication factor of 10 can be called into play when needed to further increase the sweep speed. Increasing the sweep speed allows for the display of high-frequency signals, which is particularly useful in radio frequency measurements. As sweep speed increases, beam intensity diminishes. This is because of the time the beam has available to excite the phosphor on the screen. Some oscilloscopes automatically compensate for the reduced intensity by increasing the brightness of the trace when higher sweep rates are selected. As was the case with the vertical vernier attenuator, check, and check again that the horizontal calibrate control is in the cal position. By using the trigger level control in conjunction with the horizontal position control, you'll be able to carefully place the starting point of the trace at the point you need on the graticule of the oscilloscope. This is particularly important when making AC signal measurements. Additionally, you'll be able to use the oscilloscope's positive or negative slope select switch to determine whether or not you trigger on a leading or falling edge of a waveform. Selecting the proper trigger source is important. Generally, you will trigger on the same channel that you are measuring. Particularly when measuring complex signals, you might find using external trigger to provide a more stable display. External trigger is preferred particularly when viewing complex video or television signal waveforms. Always select line trigger when making measurements related to the AC power line or mains. This is particularly useful when checking ripple, for example, on an AC power supply. You must always use extreme care when connecting the oscilloscope to the AC power line, as an extreme shock hazard is always present. In this section of DC voltage measurements, we'll concentrate on measuring the voltage of a simple penlight AA cell. You can use the techniques you'll learn here to measure just about any DC source, including a car battery or a DC power supply. Just in case you forgot, an alkaline AA cell has an open circuit terminal voltage of approximately 1.5 volts. Before we actually start taking any measurements, it's best to preset the oscilloscope controls, as we'll see here. This is where it's important to have the oscilloscope operating manual handy. We'll begin by powering up the instrument. Begin by selecting channel A on the vertical mode switch of the instrument. You'll only need to use one channel for this measurement. Set the horizontal sweep rate control to 1 millisecond per division, or 1 ms per division. Don't forget to turn the horizontal sweep rate variable vernier control to the calibrate position. Controls of this type usually have a detent at the cal position with an identifiable click sound when you reach this position. For now, you can't go wrong with setting the vertical position control to the approximate center position. Set the trigger source control to internal, and if your scope provides a choice, select channel A. For now, select positive trigger slope.
Place the trigger level control in the center of its range. If your scope has a free run mode, enable it now. For DC measurements, this setting is not critical. Turn the intensity control clockwise until the trace appears.
Keep the display brightness at the minimum necessary to prevent burning the phosphor on the screen.
Adjust the focus control for the sharpest trace. Keeping the brightness control low will help in obtaining a sharp trace. Set the coupling switch to the DC or direct current position. Connect the test probe to the BNC input connector of channel A. If you use a scope probe, select the 1X option for now.
You'll need to push and twist the BNC connector onto the front panel jack of the oscilloscope. This will ensure it is seated firmly and making good electrical contact.
Set the ground reference trace to the exact center of the screen using the vertical position control. Verify that the vertical attenuator variable vernier control is in the calibrate position. Connect the test leads to the device under test, in this case the penlight battery.
The red test lead is connected to the battery's positive terminal, and the black test lead is connected to the battery's negative terminal.
Note the noise that occurs from making poor connections. Now a solid connection to the battery has been made. Here we see the trace has deflected 1.5 divisions up from the center zero reference.
Because each major division is 1 volt, the DC voltage is 1 volt per division multiplied by 1.5 divisions of deflection, or 1.5 volts. We know that each division vertically is worth 1 volt because the vertical attenuator control is set to 1 volt per division. Let's take a look at the effect of the vertical attenuator variable vernier control for a moment. What we notice is the trace deflection decreases as the control is rotated counterclockwise. This occurs even though the battery voltage remains constant at 1.5 volts. This is why it's always important to keep the vertical attenuator variable vernier control in the calibrate position. You'll notice that serious measurement errors can occur if the vertical attenuator variable vernier control is in any position other than the calibrate position. For ordinary voltage measurements, the vertical attenuator variable vernier control should always be kept in the calibrate position. Only for special measurements such as measuring the phase of a waveform should the control ever be removed from the calibrate position.
Let's change the vertical attenuator control to a lower setting for better resolution. It's just like switching to a lower range on a multimeter. But first, let's reset the ground reference trace to the lowest point on the graticule. To do this, select the ground option using the coupling switch. We'll use the vertical position control to set our new ground reference. Now the vertical deflection is 7.5 divisions from the ground reference trace. Counting the divisions is just like reading a ruler.
Since each major division is 0.2 volts, the DC voltage is 0.2 volts per division multiplied by 7.5 divisions, or 1.5 volts.
Let's take a look at that again. Hit the channel A ground switch, use the vertical position control to set your reference, unground the channel A input, and take your measurement.
You can also short the test leads together. This accomplishes the same thing as selecting the 0 or ground switch for the channel A vertical input. Personally, I'd rather hit the ground switch. Shorting the test leads together wastes time. Even if you decide to use the shorting method, you'll still need to use the vertical position controls to set the ground reference trace. The accuracy of your measurements depend heavily on your ability to carefully set the ground reference trace. Choosing the proper vertical attenuator setting is important. Selecting too low of a setting results in the trace deflection going beyond the measurement capabilities of the oscilloscope. This would be analogous to selecting a range for a VOM that is too low for the signal being measured. In the case of an analog VOM, this would cause the pointer to deflect beyond its normal limits, possibly damaging the movement. In the case of the oscilloscope, although you won't damage the instrument by allowing the trace to deflect off the screen, you can't read it either, so it doesn't make sense. Setting the vertical attenuator control to the lowest setting possible without allowing the beam to deflect off the screen will provide you with the best measurement accuracy. Selecting too high of a vertical attenuator setting compromises resolution. Try to avoid this whenever possible. It's easy to use the vertical attenuator setting and the oscilloscope screen to determine the signal's amplitude or voltage. In this example, the vertical deflection of the beam is 3 divisions from the ground reference point of the trace. Note that the vertical attenuator control is set to 0.5 volts per division, or 1/2 volt per division. Since each major division is worth 1/2 volt, or 0.5 volts, and the beam deflects 3 divisions, the total signal deflection is 1.5 volts. Changing the vertical attenuator control to 1 volt per division further reduces the resolution, affecting our measurement accuracy. In this case, the beam is only deflected 1.5 divisions from the ground reference trace. Remember, the new vertical attenuator setting is 1 volt per division. Since each major division is 1 volt on the graticule, the DC voltage is 1 volt per division multiplied by 1.5 divisions of deflection, or 1.5 volts of amplitude.
You can make similar DC voltage measurements using a 9-volt battery or other DC sources.
Note how I'm connecting the test leads to the 9-volt battery. In the inset on the screen, you can see the DC voltage measurement as displayed by a digital volt-ohm milliamp meter. In this example, the beam is deflected 4.5 divisions vertically from the ground reference point. The vertical attenuator setting is set to 2 volts per division. Since each major division is worth 2 volts, the DC voltage is 2 volts per division multiplied by 4.5 divisions, or 9 volts.
In this measurement example, I'm using a scope probe. Most scope probes have a removable locking clamp that exposes a pinpoint tip. You'll find this handy in taking measurements in crowded locations. The tip is very sharp, so be careful when using this probe. Here I'm using the scope to measure the open circuit voltage of an automotive battery.
The digital voltmeter confirms the measurement. It looks like a 2 volt per division setting of the vertical attenuator will provide me with the best resolution. I could also use the 5 volt per division setting, but it'll compromise my accuracy. The oscilloscope can also measure negative voltages. Just use care because the case ground of the instrument is tied to the building ground. To measure negative DC voltages, we'll need to move our ground reference trace to the top of the graticule instead of the bottom. The trace deflects 2.5 divisions down from the top reference, indicating a negative voltage. The vertical attenuator is set to 5 volts per division. The actual trace deflection is 2.52 divisions. At 5 volts per division, this equates to a minus 12.6 volt reading. It was difficult to actually read 2.52 divisions. Let's switch down instead to 2 volts per division, where the beam now becomes deflected 6.3 divisions from the ground reference point. The 2 volt per division setting of the vertical attenuator gives us the best resolution for this signal. 6.3 divisions of deflection at 2 volts per division results in a 12.6 volt reading. Don't forget to carry along the minus sign. I'm confirming the oscilloscope reading using a digital volt-ohm milliamp meter, or DVOM. Note the negative voltage annunciator that's lit in the display. This tells us the signal polarity is negative. In the case of dual trace oscilloscopes, channel B is another vertical input to the oscilloscope. It functions identical to that of channel A, except it also allows the operator to invert the signal for special measurements. In the case of single channel measurements, we can use either channel A or channel B to conduct the measurements. Setting the ground reference and taking the measurement works identical to that of channel A. Varying the horizontal sweep rate, or time per division control, changes the rate at which the beam scans the screen. Slower sweep rates cause the beam to move across the graticule more slowly. This is useful for displaying low-frequency signals. Especially when the sweep speed of the beam is so slow, it's important to keep the trace intensity control to the minimum necessary to make your readings.
In this section, we've learned the scope can be used to make DC measurements. Never exceed the maximum input voltage stated on the front panel B and C connectors. Keep the intensity control at the lowest level possible that allows you to make an accurate measurement. This will prevent damaging the screen. Always select DC coupling when making any DC measurements. Always verify the vertical attenuator variable control is in the calibrate position. Failure to do so will result in measurement errors. Don't strain test probes since they are easily damaged. Use the lowest vertical attenuator setting possible. You don't want to push the trace off the screen. Use care when setting the ground reference because this affects measurement accuracy.
Now it's time to take a short section quiz to test your grasp of the material. The purpose of the intensity control is to A. Adjust vertical attenuator gain, B. Set the trigger level, C. Adjust trace brightness, or D. Adjust screen backlight intensity. If you chose choice C, adjust trace brightness, you're correct. The ground reference is always set to the bottom of the graticule. True or false?
The correct answer is B, false.
A technician needs to measure a DC voltage around 9 volts. For best measurement resolution, the technician should set the vertical attenuator control to A. 10 volts per division, B. 5 volts per division, C. 2 volts per division, or D. 1 volt per division.
If you chose choice C, 2 volts per division, you are correct.
For this question, a technician needs to measure a DC voltage around 15 volts. For best measurement resolution, the technician should set the vertical attenuator control to A. 10 volts per division, B. 5 volts per division, C. 2 volts per division, or D. 1 volt per division.
If you chose choice C, 2 volts per division, you're right.
In this question, technician A says the vertical attenuator variable control can be set in any position without affecting measurement accuracy.
Technician B says this control must be placed in the calibrate position when making voltage measurements. Who is correct? Technician A, Technician B, both technicians, neither technician.
If you selected technician B, you're correct. The switchable probe takes the place of two individual probes, a 1x or a 10x.
Fixed attenuator probes are available in 10x and 100x models. The 10x attenuator probe is used in a variety of general-purpose measurements. The advantage of using an attenuator probe is reduced circuit loading.
The standard input impedance for a scope's vertical channel is 1 megohm.
Using a 10x probe, the input impedance is raised to 10 megohms. This results in significantly reduced circuit loading, which affects measurement accuracy.
Circuit loading can cause you to measure lower than actual voltages because the probe and/or instrument provides a parallel impedance across the circuit being measured. This parallel impedance provides an additional current path through the probe or instrument, causing the voltage to fall in accordance with Ohm's law.
Reducing the loading effect helps eliminate changing normal circuit parameters during the course of the actual measurement. Accordingly, measurement accuracy is improved. For the best measurement accuracy, always try to use a 10x probe, especially around sensitive circuitry.
Use 1X probes or direct test leads for measuring non-critical, low-impedance sources like power supplies or batteries.
10X probes offer lower capacitive loading effects compared to 1X probes. This is especially critical when working with RF circuits. Even a 20 PF load can significantly alter sensitive RF tank circuits. Here is an example of a fixed 10X attenuator probe. Note the attenuator unit that is part of the BNC connector. The BNC connector is the standard for scope connections. The ground lead is supplied with an alligator clip. The lead is usually removable from the probe. The hook clip is a very handy tool for making a variety of connections.
Most attenuator probes have a removable probe tip, just like the 1X models, exposing a sharp piercing tip. Sharp piercing probes are especially useful when making measurements to printed circuit boards. Just make sure you don't slip with a probe tip. You can cause extensive damage to the circuit under test. Here the technician is connecting the attenuating unit to channel A's vertical input.
Here's the 10X probe in action, measuring a 9-volt battery.
The probe itself is connected to the 9-volt battery's positive terminal, while the ground connection is connected to the battery's negative terminal.
With the scope at 2 volts per division, the trace hardly moves off the ground reference.
Instead of 2 volts per division for the vertical attenuator, we'll choose 0.2 volts per division. With the effect of the 10X probe, this effectively takes us back to 2 volts per division. Let's take a closer look at the graticule. Note the ground reference trace must be precisely placed in order to take an accurate measurement. The actual trace has moved up 4.5 divisions vertically from the ground reference trace. This is the actual DC level of the signal. Here I'm verifying that the ground trace is sitting precisely at the bottom line of the graticule of the oscilloscope. Again, I'm confirming the signal's actual deflection is 4.5 divisions up from the ground reference trace.
Measuring a 12.5 volt DC source with a 10X probe works the same way. You must multiply the vertical attenuator setting by 10 to obtain the correct measurement. We set the vertical attenuator to 0.5 volts per division. But we're using a 10X probe, so it's really 5 volts per division.
Connecting the signal to the scope's channel A vertical input gives us 2.5 divisions of vertical deflection from the ground reference trace at the bottom of the CRT graticule. Since we effectively have a vertical attenuator setting of 5 volts per division because of the 10X probe, 2.5 divisions of vertical deflection multiplied by 5 volts per division gives us a DC signal level of 12.5 volts.
Although you have to do a little bit of math when using a 10X probe, it is usually a better choice. Before you know it, you'll be doing the math in your head automatically. But wait, what about probe compensation? I've heard about it, but exactly what is it?
Well, Janie, we'll discuss probe compensation in a later section when it's more relevant to the subject material. By the way, the accompanying technical training manual has some great resources where you can buy probes and where you can get them repaired. Check it out.
Before getting into taking precise sine wave measurements, let's examine the sine wave as a time-varying signal. This is a sine wave. It follows the mathematical sine function you learned in trigonometry. Unlike the battery, whose signal is constant and doesn't vary over time, the sine wave does. It is obvious the amplitude of the signal changes over time. In other words, voltage changes over time. The slow sweep speed allows us to see the changing amplitude over time more clearly. Watch closely. The signal is a very slow changing waveform, but it still traces out the familiar sine function. Now it's time to speed the signal up a little. We're going to increase the rate the signal changes. This is easily accomplished by changing the frequency setting on the function generator. Faster. Faster yet.
And even faster.
An analog voltmeter confirmed by the scope.
This time we'll use a center zero reading meter to better illustrate the activity of the sine wave revolving around the zero reference point. As you can see, the meter pointer revolves around the center zero point, going above zero on the positive half cycle and below zero on the negative half cycle. You'll notice as the voltage change rate or frequency increases, the meter becomes almost useless. The oscilloscope, however, continues to trace out what the signal is actually doing, even though the analog voltmeter can't see it. That's because things are just going too fast for the ballistics of the pointer. Remember, the analog meter takes an average of the signal's characteristics. As the voltage change becomes quicker, the meter can't see the unique qualities like the scope can. You'll find the oscilloscope indispensable when the need arises to look at how the amplitude changes over time, something an analog or digital meter just can't do. Now it's time to take a closer look at the sine wave itself. The signal you see on the scope trace is a complete cycle of a sine wave. It's called one full cycle. The time needed to complete one full cycle is called the signal's period. The period of the waveform is measured in seconds, but could be measured in milliseconds, microseconds, or nanoseconds. We can divide the full sine wave cycle into a positive half cycle and a negative half cycle, as indicated here. Any point of the signal that goes above the center reference line is considered to be a part of the positive half cycle, while anything that goes below that reference line is considered to be a part of the negative half cycle. Frequency is simply the number of cycles per second. Many years ago, frequency was measured in cycles per second, kilocycles per second, or megacycles per second. The unit cycles per second has been replaced by hertz, or Hz. The unit prefixes kilo, mega, and giga are still used, and so now we have kilohertz, megahertz, and gigahertz. It's important that you understand that the oscilloscope does not display frequency directly, but rather time. You'll need to make the conversion from time to frequency. Once we know the time necessary to complete one cycle, we can easily calculate frequency. The formula is simple. Frequency equals 1 divided by the time needed for one cycle, or F equals 1 divided by T, where F is the frequency in hertz and T is the time in seconds. The first thing you'll need to do to calculate a signal's frequency is to measure its period, the time necessary to complete one cycle. This is easily accomplished, just like measuring a DC voltage, except now it's time. Just count the divisions horizontally for one complete cycle, just like reading a ruler. In this case, note that there are 10 large horizontal divisions. Just like measuring amplitude, in order to determine the period or the time for one complete cycle of this signal, we need to know how much each major division is worth horizontally. So we need to check the horizontal sweep rate control setting. This control sometimes is called the time per division control. In this example, the horizontal sweep rate control is set to 0.1 milliseconds per division, so that means each major division horizontally is worth 0.1 milliseconds. Our sine wave occupies 10 large divisions horizontally. 10 divisions multiplied by 0.1 milliseconds per division equals 1 millisecond, so the signal's period is 1 millisecond. This means it takes 1 millisecond for the sine wave to complete one cycle. The frequency of the sine wave is easily calculated by using the formula F equals 1 divided by T. So in our example, f equals 1 divided by 1 millisecond, or 1 divided by 1 times 10 to the minus 3 seconds. Therefore, the frequency of the signal is 1,000 hertz, or 1 kilohertz. Notice I can vary the amplitude of the signal without changing its frequency. If, for example, this signal were in the audible range of frequencies, varying the amplitude would be varying the loudness of the signal, but the pitch or frequency of the signal would remain constant.
Without changing anything about the signal, we can change the horizontal sweep rate control setting. This results in compressing the waveform if the sweep rate is decreased.
Even though the signal looks completely different at the various horizontal sweep rate control settings, you need to realize that the frequency is constant. We're just changing the way it's displayed by varying the scope settings. We're switching to progressively slower and slower sweep speeds.
Here the sweep is disabled. This is a great way to measure peak-to-peak amplitude of a sine wave. So just how do you measure the voltage of a sine wave? You need to set the vertical attenuator just like when measuring DC voltages. In this case, using a 1x probe, the vertical attenuator is set to 0.2 volts per division.
If we were using a 10x probe rather than a 1x probe, we'd have to multiply the vertical attenuator setting by 10. Now each division is worth 2 volts per division rather than 0.2.
There are 3 common sine wave voltage measurements: peak-to-peak, peak, and RMS, or root mean square.
In this example, we have 8 divisions of vertical deflection from the uppermost positive peak of the waveform to the lowermost negative peak of the waveform. Since our vertical attenuator is set to 0.2 volts per division, and we have 8 divisions of vertical deflection, this results in a 1.6 volt peak-to-peak waveform amplitude.
All we have to do is multiply 8 divisions by 0.2 volts per division, which gives us 1.6 volts peak-to-peak.
The sine wave's peak voltage measurement is simply half of the peak-to-peak value, or from the center of the reference of the trace to the uppermost positive peak of the waveform. In this example, the sine wave's peak voltage is 4 divisions from the center reference ground trace.
4 divisions multiplied by 0.2 volts per division gives us 0.8 volts peak.
You can also measure the peak-to-peak voltage of the sine wave and divide it by 2. The root mean square, or RMS voltage of a sine wave, is 70.7% of the peak voltage. To get the RMS value of a sine wave, multiply the peak voltage of the sine wave by 0.707. RMS is the equivalent DC heating value in a sine wave. You can consult an electronics textbook for more information about RMS calculations. To summarize RMS calculations of a sine wave, multiply the peak voltage by 0.707 to obtain the RMS value. To get back, take the RMS value and multiply it by 1.414, or the square root of 2, to get the peak voltage. Let's check and see how well you've mastered the material in the preceding section. Suppose the vertical attenuator is set to 0.5 volts per division and a 10x scope probe is connected. If the signal occupies 5 divisions vertically, what's the peak-to-peak voltage?
The choices are 12 volts peak-to-peak, 50 volts peak-to-peak, 25 volts peak-to-peak, 0.1 milliseconds peak-to-peak. The correct answer is choice number 3, 25 volts peak-to-peak.
Try this one. If the horizontal sweep rate control is set to 0.1 milliseconds per division and a complete cycle of the sine wave occupies 7 divisions, what's the signal's period?
Your choices are 1 volt, 50 hertz, 0.1 hertz, or 0.7 milliseconds. If you selected choice 4, 0.7 milliseconds, you're correct.
Try your hand at this one. What's the signal's frequency in the prior example? 50 Hz, 1428.57 Hz, 1000 Hz, or 1.414 volts peak to peak? If you selected choice 2, 1428.57 Hz, you're correct.
Try this one. If a sine wave measures 10 volts peak to peak, what is the RMS equivalent?
Your choices are 1.414 volts RMS, 2.828 volts RMS, 3.53 volts RMS, or 1.414 Hertz. If you selected choice 3, 3.53 volts RMS, you are correct.
Here's another one. Which of the following probes has the smallest loading effect? Ordinary test probes, a 1x scope probe, a 10x scope probe, or a 50 ohm coaxial test lead. The correct answer is choice 3, a 10x scope probe.
In case you've wondered, we've been using a function generator for producing all of our time-varying waveforms. There are many different models of function generators to choose from.
There are, however, many ways to generate signals. Unfortunately, this subject content is beyond the scope of this technical training video. Consult an electronics text for more information.
For this section, we'll use the Leader LS1040 high-performance analog oscilloscope. Let's first power up the instrument. The power LED illuminates, indicating the instrument is on. The backlight illumination switch allows us to select no backlight or choose from 2 levels of backlight illumination.
Because we're in a well-lit room, we'll leave the backlight off.
Advance the intensity control to make the trace visible on the screen. For the best measurement accuracy, keep the trace intensity down to the minimum level necessary. Using the focus control, adjust for the sharpest trace possible. Since this is a dual-channel oscilloscope, we have 2 identical input coupling switches and 2 identical input BNC connectors.
We're going to use the channel A input, and with it, channel A's vertical attenuator and vertical position controls.
Rotating the vertical position control allows me to place the ground reference trace at any point on the screen.
Here we've positioned it at the exact center of the screen.
Don't forget to verify that the vertical attenuator variable vernier control is in the calibrate position. Otherwise, you'll affect measurement accuracy.
We'll verify that the vertical mode switch is in the channel 1 position.
We'll set the coupling switch to DC, the source to channel 1, and the slope to positive.
We'll leave the horizontal sweep rate at 2 milliseconds per division for now.
The horizontal position control allows us to position the trace on the screen horizontally. For now, let's just leave it in the center.
I'll connect the scope probe to the channel A input.
Because we're using a 10x scope probe, we need to compensate the probe. We use the cal source provided internally by the oscilloscope. This signal for this unit is approximately a half a volt peak to peak at about a kilohertz. I need to reduce the vertical attenuator setting so I can get a measurable signal on the screen. I'll also probably have to adjust the horizontal sweep rate control. If the signal is too compressed, I won't be able to effect a correct adjustment. I'll select DC coupling at the input coupling switch, and I'll use a small alignment tool to actually make the adjustment. When I increase the vertical amplifier sensitivity by switching down the vertical attenuator range switch, my trace went off the screen. I'm using the vertical position control to bring the trace back to a usable position. Now I need to adjust the horizontal sweep rate, but the trace is walking across the screen. I'll adjust the trigger level control to stabilize the trace. As you can see, rocking the control either way pulls me in and out of sync. Now I can get to the business of compensating the probe. By rotating the small capacitor in the BNC connector of the probe, I can move the compensation from overcompensating to undercompensating. I want nice square waves.
We'll connect the scope probe to the output of the function generator.
For low-frequency measurements, the connection scheme's pretty unimportant.
Make sure the input coupling switch is in the ground position. Set the ground reference trace to the center of the screen.
Switch to AC coupling and then move the vertical attenuator setting to a range more suitable for the signal. You might need to increase the intensity a bit to see the signal. If the vertical attenuator is set too low, the signal will be out of limits of the graticule. This is a more reasonable setting for the vertical attenuator. Readjust the intensity appropriately. Try to allow only one cycle of the wave to appear on the graticule if possible. You'll need to try different settings of the time per division or horizontal time-based control to accomplish this. As you can see, the signal doesn't start at a point that's convenient for taking measurements. By adjusting the trigger level control and horizontal position control, we can manipulate the signal so it starts at a more convenient point for taking our measurements. If I rotate the trigger level control out of range too far, you'll notice that the signal loses synchronization and begins to drift across the screen. You'll need to experiment with this control to become familiar with its operation for your particular oscilloscope. Now I've positioned the waveform on the oscilloscope screen so that the start of the wave begins at the leftmost graticule marking. This is important because I need a reference point where the signal begins. I can line the start of the waveform up on any convenient mark on the graticule, but I prefer to be able to use the full oscilloscope display, so I generally choose the leftmost portion of the screen. I'll hit the ground position of the coupling switch and just verify my center ground reference trace. I've noticed that the trace is not perfectly parallel to the horizontal lines of the graticule. I'm going to use my alignment tool to trim up the trace a bit using the trace rotation control. This is usually one of those set it and forget it settings. I'll switch to AC coupling and now I'm ready to take a look at the signal. I've deliberately made it that one cycle fits the screen exactly. You can see the effect on the signal when I vary the frequency control of the function generator. You'll notice that even though I'm changing the actual period of the waveform, which obviously changes the frequency of the waveform, the amplitude of the signal remains constant. If I vary the frequency of the signal too far, though, I'm going to have to change the time per division or horizontal time-based setting. If I change the horizontal time-based setting to a point that allows me to display 2 cycles of the signal rather than 1, you'll note that I may have to manipulate the trigger level control and horizontal position to position the wave at the beginning of the graticule. The problem with displaying more than 1 cycle of the signal on the screen is obvious. It's difficult to get an accurate period measurement when more than 2 cycles of the signal are being displayed on the graticule. Here I'm trimming up the frequency a bit so that the wave occupies exactly 10 divisions horizontally from start to finish. If you're going to be making an amplitude measurement, you're probably going to have to slip the vertical position control a bit. This is necessary so you can position either the top positive peak of the wave or the negative bottom peak of the wave on a major horizontal line. This just makes it more convenient to take the measurement. Remember, your zero ground reference is no longer going to be in the center of the screen. In the example, the vertical attenuator control is set to 0.2 volts per division, but remember we're using a 10x probe, and we're seeing 5 divisions of vertical deflection from the positive peak to the negative peak, so the signal's peak-to-peak value is 10 volts. I'll switch the input coupling selector to ground so I can return my ground reference trace to the center of the screen. Now the sine wave floats equally above and below the ground reference trace located in the center of the screen. I can adjust the amplitude of the signal at the function generator without affecting the frequency. I'll change the vertical attenuator setting to 0.5 volts per division, and with a 10x probe this brings it to 5 volts per division. And I'll increase the signal's amplitude a bit more. If I try to switch down to 0.2 volts per division with an effective attenuation of 2 volts per division as a result of the 10x probe, you notice the signal goes out of limits of the oscilloscope graticule. What I need to do is go back to 0.5 volts per division, and with the effective multiplication of the 10x probe, this will take me back to 5 volts per division. With 4 divisions peak to peak, I've got a 20 volt peak to peak sine wave displayed on the screen right now. To locate these points more easily, you might find it convenient to slip the trace to the left or right a bit using the horizontal position control. You can then use the crosshairs in the center of the screen to take an accurate measurement. Now I've increased the signal's peak-to-peak amplitude to occupy 6 divisions vertically. At an effective 5 volts per division vertical attenuator setting, taking into account the 10x probe, we have a 30 volt peak-to-peak signal here. Now I'm going to increase the frequency of the function generator by pushing in the next decade range switch. This effectively multiplies the frequency reading by 10. You'll notice, except for taking a peak-to-peak voltage measurement, it's impossible to measure the period of this signal. We'll need to change the time per division or horizontal sweep rate control to expand this waveform so we can get an accurate reading. You'll see turning the horizontal sweep rate control counterclockwise is actually going in the wrong direction. We need to expand out the waveform, so we need to rotate the control clockwise. As before, use the trigger level control and the horizontal position control to start the wave at the leftmost mark on the graticule. I'll trim the frequency a bit so the wave occupies exactly 10 divisions horizontally. With the horizontal sweep rate control set to 10 microseconds per division, this means each division is worth 10 microseconds horizontally, and we're occupying 10 divisions, so the overall period of the wave is going to be 100 microseconds. If we change the slope from positive to negative, we see that the waveform begins tracing on the downward descent of the wave rather than the positive ascending side of the wave. Remember, the 10x probe has nothing to do with the horizontal time base whatsoever.
Here's an example of a low-frequency triangle wave. Measuring amplitude and period of a triangular waveform is done in essentially the same manner as that of a sine wave.
As you can see, the brightness decreases as the frequency of the signal increases, so we need to increase the trace intensity a bit. Of course, if we increase the horizontal sweep rate, the intensity will also decrease, so we'll need to make an adjustment there to compensate. Period is best measured by expanding the horizontal sweep rate as much as possible, while still maintaining at least one complete cycle on the screen.
This is an example of a square wave. The square wave is usually considered to be a digital on-off signal as shown here. It takes on only 2 states, a logic 1 or high voltage, sometimes referred to as the high state, or a logic 0 low voltage state. This is usually 0 volts. Here we're increasing the frequency of the square wave. Rise time of a square wave is extremely short. The signal should not exist in any state other than a 1 or a 0.
The signal changes so quickly from one state to the other, the beam doesn't have enough time to illuminate the phosphor. With high-speed scopes, it's actually possible to measure the rise time of the waveform.
Applications for square waves are numerous: digital timing, computers, digital logic ICs, automotive, signal processing, and more.
More information relating to square waves, including pulse width measurements, will be presented in the next technical training tape currently under development.
The next technical training video will contain advanced topics such as dual trace measurements, pulse width and duty cycle, phase shift, power supply ripple, and rectifier measurements. We'll even explore some automotive-related signals you can measure with a scope. We hope you've enjoyed this technical training videotape.
And we hope to see you in future programs. For SciSpec Technical Training, I'm Richard Kent.
And I'm Janie Kent. Thanks for watching.